Right, so we should start the talk. So welcome, Thomas. Thomas is a master's degree in a TPH in Sweden and a doctoral student at the University of Sweden. And now you will be something about privacy in large language. So thank you so much for joining me in this. I was the last talk about privacy. A lot of
thanks for inviting me. So yes, as you just mentioned, I'm Thomas Vakili, so I'm from Stockholm University, and I have a background in computer science and engineering. Now I focus more on natural language processing. So I've been here in Santiago since September. Unfortunately, I leave next week, but my stay here has been lovely. And I've been supervised by Professor Jocelyn Dunstan, who is at CNN and also at the Catholic University while I've been here. So that's been very nice. In Sweden, I'm supervised by Professors Helgius Danialis and Aron Henriksson. And I will return to continue working with them in the next week. And where I work is, as I mentioned, in Stockholm, so it's far north, a long way from here. And now it's actually winter there, so I have a friend texted me this morning that it's minus 17 degrees there. Not looking forward to that. But our department is a computer and system sciences department with around 5,000 students, so it's quite big. And we also have around 45% women, so we're quite good on gender equality, which I think is a nice thing about our department. And I will be talking about privacy and natural language processing, but I will have like a special focus on clinical data, because at our department we have a really big resource of electronic health records. And if you're not familiar with those, it's like when you visit the doctor, they write about the visits and they record this information. So we have like 18 gigabytes around of raw text, millions of these records. And then we also have other more structured data like lab measurements, we have diagnosis code, etc. I focus mostly on the textual data because that's what's most useful for NLP. But we've used all of these different modalities to build several different resources that we have constructed during these years. So these are some examples, and we've been working with researchers from many different labs, both in Sweden and outside of Sweden, to conduct research using this quite unique resource, I would say. And with that out of the way, this will be the basic structure of the talk. I will talk a little bit about large language models and the theory why they work, and then move on to the privacy risks of LLMs, and also then end by talking about ways that we can protect privacy. And what is everybody's background here? Are you like computer scientists, all of you, or?
Not from law school.
Okay, perfect. Then it would be great that I also have this introduction, I think. So let me know if you have any questions. It's not going to be super theory heavy, but I will give like a brief intro. So it's not like essential to understand everything going on this slide. What I want to show with this slide is basically that the way AI is being hyped a lot in the media, it sounds like there is some magic going on. But in reality, all networks basically are based on two things, matrices and matrix operations, and then nonlinear activation functions. And that's basically like anything that's not a straight line. And while not everybody knows about this, it's nothing like beyond what you learn in maybe the first year of an engineering program. So this is good to keep in mind when you're listening to this topic, but also like reading the media about like ChatGPT and these new advances. And the idea why this works is that there is a theoretical idea called the universal approximation theorem, which essentially says that if you have a neural network with one layer and enough training data and parameters, then you can approximate any function. And a function could be like in like typical high school math, that you go from one number to another number, but it could also be something more interesting, like taking a picture of a cat, for example, and assigning it the label cat. So a function should be understood in this more broader sense. And the important caveat is that you have to have enough training data and that the network is big enough for this theoretical result to hold. But in practice, we find that with the modern implementations that we have, we can get quite close to this. And we also, when we talk about neural networks, we talk about training them. So training is finding like the optimal values for these values in the matrix that allow us to have this function that maps from our input domain to what we want to achieve. And we call these values parameters, and then we learn them from training data. And this training is often done to perform a specific task. And to illustrate what tasks we would have perhaps in natural language processing, which is the main topic, you can more or less divide them into three main topics. One is that we have documents and we want to assign labels to the entire document. This is called classification. So in this example, we have an electronic health record, and then we want to assign it the appropriate diagnosis code. Another example is tagging, and here you're not assigning a label to an entire document, you're assigning labels to specific words or series of words in the document. So here we have clinical entity recognition, where we find like clinically relevant terms. So we might be interested in finding all of the drugs mentioned, for example. So we have paracetamol there. And then the final objective, which is very popular now and growing in prominence, is generation. The generation is not assigning labels, it's generating new text from the text that you have. And an example, for example, is here we could think of an electronic health record, and maybe we want to have a system that makes this information easier to understand for the patient. So then we have like a simplifying generative model. And in general, we have to solve a series of different steps to do successful NLP systems. So one is how we go from our textual inputs into numerical representations. And the first step is to do this on the word level. Then we need to relate the words to each other, because just considering words in isolation is usually not enough for a lot of tasks. And in this example, we have the task of sentiment classification, which is when we take a sentence and when we assign it, label it, it's a positive sentence or a negative sentence. But to do this, we have to solve all of these steps. And in more traditional deep learning up until like 2017, the typical way was that we had like pretty good solutions for the word level. So we could go from words to numerical representations, but then to relate the words to each other and solve the specific task, then we had to use label data. And label data is data that typically a human has been sitting down and annotating manually. And this is really expensive to create. So one of the main breakthroughs with these transformer models that are very popular now is something called pre-training. And the idea there is that you don't need this carefully manually constructed data set to solve the sequence modeling steps and the word modeling steps. Instead, use a big body of text that you could, for example, download from Wikipedia or other websites. Typically, it's web data. And then you do something called pre-training, where you teach a model to do word modeling and sequence modeling. And then you usually need a lot less label data to solve a specific task. So either you will need less data, so it's less expensive to create, or you can achieve even better results with the data that you already have. So this was a huge breakthrough. And I've been mentioning the word language models a lot. Essentially, you can think of a language model as similar to your autocomplete in your cell phone. So language models are trained to predict the most probable word. Typically, this is done left to right if it's a language like Spanish or Swedish, where we write left to right. And the GPT family of models that are used in ChatGPT, for example, they are this kind of model that predicts from left to right. And we can call them autoregressive models or generative models. There are different ways of talking about it. But essentially what they're doing is that based on the words they have seen, they are going to predict the most likely next word. That's essentially the idea. There is another type of model as well, which is called a masked language model. And I mentioned this because I've used BERT, which is one prominent example. I've used BERT a lot in my research. So Instead of predicting words from left to right, what BERT does is that it takes a sentence with a gap somewhere and then it predicts what should be in the gap. So if you've done like you studied foreign languages before, this is quite a common thing that you do in your textbook. So here the models should predict that I'm a PhD student and not something else. So this is another way of learning to model words and sequences. And then the final part then of large language model is the large part. So essentially there are two aspects to this. One is the amount of parameters, so the number of values in all of the matrices. And in this BERT model, the large one from 2018, we had 340 million parameters, which is already quite a lot. And this graph is actually a little bit old now, but in 2021, so 2 years ago, they released a model which was almost 1,000 times larger. So this has been growing really, really quickly. And you can see here that this, the axes are like logarithmic, so it's like exponential growth. You can also see GPT-3 here, which used to be what powered ChatGPT. It's a lot less than this model, and now they have ChatGPT-4, and we don't even know how big that model is. I would guess that it's probably more on this scale. But apart from the number of parameters, it's also the number of words that we use to train the models. So for BERT, we had 3.3 billion words. For this newer model, the Megatron Turing NLG, we had 270 billion words. So this is a lot more text than we could expect any human to manually go through an audit. So we're dealing with huge scales here. And this is one of the main reasons for why we have privacy risks. And the main privacy risk, I would say, arises due to something called memorization. So because we have these large number of parameters and that we have a training objective, which is essentially to reproduce the training data, sometimes this leads to a degree of memorization. So when specific parts of the data are memorized in the matrices. And you can think of examples where this could be partially useful. So, for example, when we're learning to relate what Chile is, for example, it's useful to memorize that it's a country in South America. So some facts about the world, we want them all to know. On the other hand, I actually don't have a root, but you could imagine that a model was trained using a data point like this. And we don't want it to memorize somebody's root number, because this is not very useful for the model to know, and also it leads to risks. Are you coming from the top or?
No worries.
Go ahead. Yeah. Okay. Yes, the privacy risks make the models sensitive to certain forms of attacks. So the most severe form, I would say, are training data extraction attacks, which, as the name suggests, are about extracting data from a model. Then there is another form of attack called membership inference. And here we're not extracting data. Instead, we have some data point and we want to figure out whether or not it was part of the data set. So this way we can determine if text we have equals real or not. And I'll start by describing membership inference attacks. So I have adapted this from a paper by Mirskala et al. From 2022. And this was a very efficient way of doing this. So the idea is that we have a training data set D that we use to create a model that we're attacking, this one in yellow here. And then we get a data point D, and then the objective is to check whether or not this data point was indeed part of the training data. So to make this easier, we can bring in a reference model, and the good thing about this model is that we know that it has not been exposed to this data point, so it has never seen it before. And then to check whether this data point is part of D or not, we feed it to our two models, and then we see how likely each model thinks that this data point is. And the intuition here is that if this yellow model had been trained using this data point, it would assign an unnaturally high likelihood of the data points. And then we do the same for the reference model, and then we can compare the differences in how likely the models think that this data point is. And if it's above a certain threshold, then we say that, okay, we found a real data point. And in this paper that I'm describing, they reached quite high recall, so they were quite accurate in this type of classifications. And if we assume that a model had been trained on clinical texts, then we know that the data is sensitive and we need to protect it. And while we can't extract data using this method, being able to perform this attack can still yield some dangerous consequences. So, for example, we could infer if a patient has visited a set of clinics, because if we know where the data is coming from, and we know, for example, one of the clinics could be related to STDs, then that would be sensitive information to reveal. We could also figure out when a patient has sought care, and this in turn could have problems if, for example, for insurance purposes. So there are some risks to this attack alone, but it's also usually a part of other bigger attacks, namely training data extraction attacks. So this is copied from a paper by Carlini et al. From 2021. And so they were attacking the GPT-2 model. So this is earlier model from OpenAI. So I would guess that most of what applies here probably applies to ChatGPT, to GPT-3, and GPT-4, because this is a much smaller model. What they did was that they generated a lot of text from the model, and then they used different form of membership inference attacks to rank how likely they thought that these generated text were to be part of the training data. And then after doing some further pre-processing, they selected a list of the top 100 most likely training data examples. And then they actually checked whether they could find these on the internet. And in fact, they did find a lot of sensitive information. Not all of it sensitive from the privacy perspective, but for example, they found some news data that was copied. This could be sensitive for copyright reasons. But then, of course, they also found like names of individuals that were not like public people, and they also found contact information to some people as well. And this data was available online. If this had been clinical data from electronic health records, it would have been even more severe. So, what can we do to protect the privacy? That final part. First, good to mention, like maybe why do we need to care about this? Like, why don't we just build models, release them to the internet, and then hope that nothing happens, as some people are actually doing now? One thing is that the law prohibits us from doing so. I'm not 100% certain how it's in Chile. I know that there is like ongoing discussions about new privacy protections.
Yeah, there is a new law, there is a new law in this the Senate, está sacando como, si me podéis traducir, está sacando varias disposiciones del GDPR.
So it's
y está como
generating
una especie de tratando de copiar un poco el GDPR para poder utilizar las normas aquí en Chile.
Kind of copying.
Yeah, my Spanish is okay, so I understand.
Great.
Yeah, nice. Yeah, and like the GDPR is very strict, so we'll see how it ends up in Chile. In Sweden, we're part of the EU, so we have to abide by the GDPR. And basically, the idea is more or less that you can't have any privacy leakage. And if you do, you will have really big fines. And if you're running a company, then that's really dangerous because it could kill your company, basically. So you need to be very mindful of this. As researchers, we sometimes have like exemptions from some of the rules. But then we also have like the ethical perspective. And so at our department, we have clinical data. It's not possible to get like informed consent from everybody who's described in the data. Even if we could ask every single patient, maybe the patient is described with some other person, like a family member or so on, and we don't know this. So getting full total consent is basically impossible. And we don't want anybody's data to be exposed, so therefore we need to care about privacy. And thankfully, there are a number of different privacy preserving techniques that we can consider. I like to think of them as like two different categories, one that is like formal and mathematical. A good example here is differential privacy, which I will describe shortly. Then we have the more intuitive and more heuristical ones, like automatic identification, which is the main focus so far of my PhD. We also have like synthesization of training data, which is, I think, is an interesting research direction. I don't have time to talk about it today, but I want to mention it anyways, because I think it's something that at least I want to work more on in the future. But getting into differential privacy on a very high level here then, what's the idea? So the idea is that we want to measure how much a data point changes a model. So if we consider that we have a data set A and a data point B, if we remove B, we can get the model A, and if we include B, then we get the model A plus B. So we have these two different models. Now, if we say that data point B was Thomas has diabetes, I don't, but it could be a data point, then we ideally want these models to be indistinguishable, because it shouldn't matter that much that we have this data point. In this example, we would probably conclude that we don't really have good differential privacy, because as you can see, the model that has included B assigns a higher likelihood than the other model. And we want to avoid this. So the idea is that when we're doing this training process, we do it in a more noisy manner. So I didn't mention this term before, but when we're training models, we have something called a loss function. So we give the model a data point, and then it will predict something. And usually it's not the exact same thing as it should predict. And then we calculate how wrong it is, basically. And this is what we use to update all of these parameters in the model to make it better. But if we are too, if the training is too powerful, that's one reason why you could get memorization. So the idea of doing differential privacy with deep learning models is that we inject some noise into this process. And by doing so, memorization becomes less likely. And another good thing about differential privacy, now I've described it with figures, but you can also define it very rigorously using mathematics, which I think is the main pro of this method. I guess the big flaw is that this is the mathematical description, and it's quite difficult to pick apart. But if you look at it long enough, you will understand it. But you also have to select certain parameters that govern how much safety you have, and these are called epsilon and delta. And it's not always clear how to choose them. So another good thing is that it works for many different data types, so it's not specific to text or images or tabular data. You can use it in many different contexts. But because we're injecting noise into the process, the models also learn slower. So you need to have more data and more compute time to achieve similar results. And also, while it's useful that it's applicable to many different data types, it also loses some power because of this. So it doesn't use, for example, some specific aspects of text data. And a way to do privacy that does this is automatic de-identification. So this is basically, the gist of it is that we detect sensitive entities. Entities can be names, they can be locations, a whole range of things. And once we've detected them, we do some form of sanitization. And this can be done in many different ways. I've highlighted two examples here, partly because I have a paper that I will describe later that uses them, but also because it highlights why you need to be careful of which approach you use. But one example is that you remove sensitive entities and the context around them. This is quite it mimics sort of how humans do when they're releasing sensitive reports. They redact it like a marking pen. The other idea is to replace the values. Sometimes we call this pseudonymization. So we find the names Frederick and the last name Moody, and we replace them with pseudonyms. So we replace Fredrik with Stefan, which is another common Swedish name, and Moody with Lundvall. And this way, we also preserve basically the meaning of the text. So although the names have changed, the overall information is almost the same. Like if we don't care about the specific persons, essentially these sentences are equivalent. But detecting these entities relies on machine learning models, and they are never perfect. So sometimes we will miss some entities, which is not good for privacy. But here we also can highlight the importance of choosing your sanitation strategy. So if we do removal, then we will still have this name Moody left in the data. This is the same for both methods. But if you're an attacker and you're looking through this data and you want to find sensitive information, if you encounter a name, then you can be 100% sure that this name is real. Because if it was not real, then it would have been redacted. So that's a downside of this approach. Instead, if you do this replacement or pseudonymization strategy, then Modig is still left here in the text. But if you're an attacker and you don't have access to this like holding, then it's not immediately clear which data is real and which is fake. So another problem is that sometimes the model will be too eager to flag information as sensitive. And in this case, we could consider that the model accidentally thinks that tibia is a location and not a bone in the body. What will happen then is that it will replace it with, for example, Stockholm, leaving us with a nonsense sentence. And the fear from some researchers has been that if we do this, then the data will become less useful for machine learning purposes because we're essentially feeding the model garbage. So this is something that we have been looking a lot at to see whether this is true or not. So as I mentioned, we have this health bank at my department containing these millions of patient records. So we ran our de-identification system on this data, and we found millions of like names, locations, and so on. And we have pretty high accuracy for many of them, but not perfect. But for first and last names, for example, we see that we have like around 97% recall and precision, which is quite high. And then we checked, so when we do this process, do we lose the usefulness of the data? Does it become less useful for pre-training, and does it become less useful for solving specific tasks? And the first thing we looked at was to experiment with specific tasks. So we have a paper where we did 3 different ones. So one was this example that I showed you earlier, where we have an electronic health record and we want to assign it a diagnosis code. Then we also had another thing where we tried to predict how certain a doctor was in his or her diagnosis. So this is called factuality classification. And then finally, we have also the example of finding clinically relevant terms, so clinical entity recognition. And what we did was we kept the original data, and then we also created a pseudonymized data, so one that where we had replaced sensitive entities. And then we created BERT models that we trained with these data sets, and then we compared if there was any difference between training on the real data or the pseudonymized data. And essentially what we found was that it worked just as well. So if you pseudonymize your fine-tuning data, you will most likely not have any negative impact on your results, which is good. And then we looked at pre-training. So here we return to these 2 sanitation strategies. What we did is that we tried both. So we tried the removal strategy, which removed, I think, around 10% or something of the data. And then we also did replacement, where we replaced it with realistic surrogate values. And then we took an existing BERT model for Swedish, but that had not been exposed to clinical data, and then we adapted it using this clinical information. Then we did even more tasks that we used to evaluate how good these models were. And once again, we found that there was no deterioration from using the safer data. So the first row here is the model that's not trained on any clinical data. As we can see, like all of the other models outperform this model, which is good. But we also see that the second row, which is the model that has been trained on real sensitive clinical data, performs basically the same as the two safer ones. And another nice outcome of this paper was that we were allowed by the Swedish Ethical Review Board to share one of the models. So this model is now known as Swedish Clean Birds, so Swedish de-identified clinical birds. And we have actually started to share it with other researchers in Sweden. I guess we could share it with you as well, but I don't know how interested you are in the Swedish clinical entity. But if you are, just let us know. So the good things with automatic de-identification is that it does improve privacy. A negative thing is that we don't know how much. So we can count how much we find. We have some sense of how accurate we are in finding this sensitive data, but we don't have this nice mathematical definition that we have in differential privacy. Other good things is that it's quite intuitive. So explaining this, I hope I did it well enough, but like you can explain it to a layperson. There is no like advanced mathematics required. Most people can understand it given enough time. And also that in contrast to differential privacy, using this doesn't make the training process that much harder. So we still retain the same amount of utility of the data while still gaining privacy. But then there's also the question, so we have a list of different entities that we consider, so like names, locations, etc. What we don't consider is like ethnicity, for example. We don't have occupational information. And these entities could also be considered sensitive. So defining a list of what you should cover is quite difficult. And some data also can't really be neatly fit into these categories, but could still be sensitive. And this approach has some trouble with like handling that kind of information. So summarizing this presentation, what I would like to have as the main takeaways. So that is, first of all, that large language models are collections of optimized matrices. There's no magic going on, but these matrices sometimes memorize training data. And then this exposes them to real attacks. So there are examples both of training data extraction attacks that work and membership inference attacks that work. So the risks are real, but we have some approaches that can be combined or used separately that mitigate some of these concerns. So the more mathematical ones, like differential privacy, and the more heuristical ones, like automatic de-identification. And which one fits your purposes depends on your context. Yes, and then we have some open questions like, could we compare these methods in a good way? There's no like set definition of how to define privacy for language models. There are some people that are suggesting some ideas, but it's there's no consensus on this. It's also not like a consensus on what data should be considered sensitive. Like we have in the US, they have this HIPAA law that like specifies certain categories, and GDPR has a more like, vague definition. We'll see what happens in Chile, but it's an open question. Then it's also like, how private do we need the systems to be? Like, you can never make something entirely safe. Some risk will always be involved if we're going to use the data at all. And this is something that needs to be defined. In the GDPR, they say that there should be no risk, which is, I think, an unrealistic expectation. And I guess this will be decided maybe in courts in Europe. We'll see. And then also, like, how good results can we get with synthetic data? Can we replace data with synthetic data? And in theory, this data is fake and it shouldn't be sensitive. But of course, as Kalin et al. Showed, sometimes the models will output their own training data. So how can we be sure that this data is more private in practice? This is something I think that needs to be studied a lot more. And here are some references that I've been using in this talk. I guess I can upload the slides later and then you can check them out. But that's basically it. So if you have any questions, let me know.
Thank you.
Thank you.
You're welcome.
I have a question about the process of automatic identification. Where does it occur on the data science pipeline? Like, as I understand, you do it before you train the algorithm. Before you train your model. And you do use another model for recognizing sensitive information. But what you end up publishing after this is the main model. Like, this is what you get from just publishing the main model that's been trained on the identified data. Okay.
Yeah, so in our case, we actually we're not allowed to share the model either. So we can just publish the description of the model basically. Because now I've talked about how you can attack pre-trained models. There are also attacks that work with the fine-tuned ones. So if we share the models that can find sensitive data, that in itself could be used to find sensitive data. So it's kind of like a loop in that sense. But usually, like in our setting, we do the de-identification before we use the data for training. But you could, of course, apply it even earlier. So you could apply it like before you store the data, you de-identify it. I think an interesting thing would be to maybe apply it even at the when you enter the data. So like in the clinical setting, like doctors maybe shouldn't write the names of the patients, like relatives, for example, because it's not so clinically relevant and it exposes the hospital to security issues. So you could apply it even there. So when the doctor is writing, it might warn them, maybe this is sensitive information, consider like excluding it. So you can apply it basically anywhere, I would say. Yeah.
All right, more questions.
So it seems what you're doing is independent of the model. You're basically anonymizing the data. How is this different to basically all the different anonymization of data sets? Because at the end, you don't care about the model itself. If your data is anonymized, then you're done. So why talk so much about the models? In fact, they are just tackling the data.
Yeah, I think the reason why we focus on the models, traditionally, I think a lot of the literature has been considering like anonymization, pseudonymization, and these strategies for the data itself and using it like for all different types of purposes, like giving it to clinicians to conduct research by reading it, for example. And to do that, then we need to have very high standards, I would say. So the reason we focus on the models is because like not everything is memorized. So our what we are looking at is whether we can achieve pseudonymization, which is not good enough that you can just publish the data like anywhere, but good enough so that if you train a model with the data, then this model can be safe. So that's the idea. A good question. Yeah.
Yeah, I have a couple questions myself. So you, in all the results that you showed, are they all based on a pre-trained model that you're fine-tuning, including the, let's say, the language modeling test? So if you could go back to those slides. So yeah, before that, so the pre-training. What do you mean with the pre-training stage? Because when I think of a language model like BERT, I imagine that it's been trained for a long time. Do you mean like it's the pre-training phase, but only on your new data set?
Yes. So what we did here is that we took a Swedish BERT model and then we used our clinical data to make it more like specific to the clinical domain.
But the model was pre-trained before that.
Yes. Okay. We have also done experiments where we use just the clinical data. What we found there was that it's basically the same results, but we did this after this paper, so we could possibly like redo those things and see. The problem is that pre-training is like so expensive, so if you really don't want to do it too many times.
Yeah, and that leads to another question. So how long did you train this model? Is there a kind of high parameter in terms of how long you have to
expose your model to the anonymized data in order to de-anonymize the model. You know what I mean?
I think we trained these models for like 3 epochs, so 3 like loops over the entire 18 gigabyte data set. So I don't remember exactly how long it took, but it was like in the scale of weeks. So
Okay.
it's quite time consuming. When we also like we're not allowed to use, for example, Google like servers to do this because the data is sensitive and we can't.
Yeah.
We have like this room actually where you have a key card and you can go in and it's like a big noisy server that you should next to this. And it has 4 GPUs, so it's quite powerful. But I mean, if you have more powerful computers, then you can do it quicker. But
Of course, yeah. And after that, so you did the fine-tuning stage on the anonymized data. But did you do that on the model that was already trained on de-anonymized data? So because if you go to that, so the last table, which you're showing, yeah. So I'm not sure if I understand the models that you're using, but is there a model in which you take a? So, but I want you. What I'm thinking about is, what if you have a model that is dangerous in terms of anonymity of the data? Can you correct that model by
like after the fact,
training it on the de-anonymized data? And so if there is any comparison regarding that.
No, so here we're not looking at the privacy risk. Now we're just looking at the performance. There are like I've seen papers before that consider like there is this concept of like unlearning, so that you get the model to forget things that it's memorized. But I saw a lot about it for like a couple of years ago when I was just starting my PhD. Now I haven't seen so much about it. I don't know if it's like they lost interest or that it didn't work. But it's an interesting, because I mean there are models already that are being shared, and some of them will contain sensitive information, so it would be very useful to prove it. But it's not something we've done.
Yeah. All right. And how about the model to de-anonymize data? Is it just a named entity recognition model?
Yes.
All right. And so how about that model? Did you just choose a good model for de-anonymization and then just stick to that model throughout the process, or did you like go back to see if improving that model would have improved those metrics on the anonymization data? Anonymization metric.
So like in the presentation, it's actually like chronologically kind of reversed to how we did the research. So for these results, we had a pretty good model, but for the other results where we had this one, we had actually already improved them all a little bit. Okay. So we were continuously trying to improve the model because we will get like more privacy benefit. But yeah, so we don't have like this, it's not published. We have a version that we are allowed to share, but the best ones are the ones still that we have just used, like the biggest ones and like with the most data. So we haven't been able to share those. All right. Hopefully we can do it.
Well, thank you.
Thank you.
Yeah, I have a question. My English is not that good. If anyone can help me with question,
yeah, sure.
Desde el punto de vista del derecho,
From the law point of view,
podemos encontrar que está la regulación de la privacidad propiamente tal.
because for regulating privacy as
Yeah.
such.
Y podemos encontrar que eso es suficiente para los modelos de lenguaje,
Is that enough for the language models,
o si es necesario una regulación específica al respecto.
or if it's necessary to have a specific regulation?
Good question. I mean, I'm not sure. Like it would maybe make sense to have either you would have like legislation that is vague enough that you can have like specific, maybe more like clarifications for different types of data. Now everybody's using this like transformer models. I mean, who knows in 5 years ago, this was a very like niche subject. If I were talking to people on the street and mentioned like, I do like language models, nobody had no idea. Now everybody basically knows about ChatGPT. So things have gone up quite quickly. They could also change very quickly. So like having two specific laws might make it so that future solutions don't really fit. So I would say maybe having a general one is a good, but then, yeah, I'm not sure. Yeah, I think it's difficult because like on the one hand, like politicians are the ones that decide these things. On the other hand, we also want some expert input, but we need to have like a balance because depending on which experts you ask, maybe they are too focused on their narrow like subject and they don't have this like broader perspective. So it's a difficult question, but it's a good thing that we need to think more about, I think. Yeah.
Thank you.
Yeah, thank you.
Very technical, but about the attacks, I was wondering, how do you get the model to do the probability of phrase? Because, like you said, that's word prediction. So, how do you get the
So
outcome?
there are different ways in this attack. This is estimated by, so the BERT models, they're trained by, you have this like mass prediction. So in this case, you calculate the loss for every different, so you put the mask in every single position, but you change it every time. That makes sense. And then you calculate the loss for each example, and then you aggregate those results. Yeah, so that's the way that it's done. And there are some more like theoretical like descriptions of why this is a good approximation. Of course, it's always like an approximation of probability. We don't have like the real probability.
Yeah.
But that's how it's done here.
Oh, any more questions?
And one last one. So when you said that these heuristic techniques have no, say, formal guarantee of working stuff like differential privacy, is there a way that you have, say, measuring how much more private let's say the model or the data, because yeah, you're changing the data, but maybe the model compression is really what you get about that.
Yeah, that's a good question. Something I didn't include, but it's great that this slide is up actually, because the idea of this paper was actually to use membership inference attacks to quantify how private a model was. So the idea is that if it is more susceptible to membership inference attacks, then it's less private. So that's an interesting idea. We actually wrote another paper afterwards where we used this idea, and what we showed in that paper was that actually this doesn't seem to work very well for pseudonymization. So in that paper, what we did was that we took this data point, for example, and instead of having like Mrs. Smith, we changed it to, I don't know, Mrs. Johnson, for example. So it was like pseudonymized, and then we have the non-pseudonymized version. And then our idea was, so if this way of quantifying privacy works, then the Mrs. Johnson version should not be classified as a real data point because we've changed it. But what we found was that this way of detecting membership basically could not distinguish between the data points. So if you use this approach to quantify how much more private a pseudonymized system is, then it will say that there is basically no privacy benefit. But of course, if you removed all of the names, like intuitively, you should consider it more private. But this doesn't really work for that. So it's still an open question.
Cool. So, are we good? Well, thank you so much, Thomas, for your talk. So let's do applause.
Thanks for the great questions. It's nice.
And yeah, I hope you have a nice trip back to Sweden.
Thank you.
Okay, cool.
Alright.